All right, let's get started. Hello. Happy Monday to all. And today I'm going to start one of the main topics in analysis and what my personal favorite. So it's chromatography. So we're going to spend quite a few lectures on chromatography. We're going to have lectures on basic chromatography, and then GC, gas chromatography, liquid, high performance liquid chromatography. So I think there will be in total about 7 to 8 lectures on chromatography. So you will be experts by the end of those. Okay, so what does chromatography mean to you? When you hear the word chromatography, what is it? What do we use it? What does it mean before what we use it for? What does it mean?
Being able to analyze like the like compounds that you're trying to figure out like the structure of it, its chemical makeup.
Yes, so analyze compounds, have an identity about structure, but what is the real, this is correct, right? But what is the principle of chromatography? What is it based on? Very simple, one word. What happens during chromatography? Michael, what?
Waves.
What?
Waves.
Oh, that's spectroscopy.
Separation.
Separation. That is the word I was looking for. Separation. So oftentimes when you're trying to analyze different compounds in a mixture, and in order for you to identify or detect or quantitate, you want to separate them from each other. Okay, so chromatography is really a method of separation. Okay, so there's a story that I always give as an example of chromatography. So listen well, it might come in one of your exams, you never know. So there was, I don't know if it still is there, a shop at the mall called Justice. The girls are laughing, the boys are, yes. So when my daughter, now my daughter's 19, so closer to your age, but when she was like 10, 11, 12, that was her favorite store and my nightmare. So there two of us, 2 compounds, 2 people. We walk into the store, a lot of pink and a lot of purple and a lot of glitter and sparkles. So we go in. I'm ready to leave in like 1 second. So I just go in. No, I'm ready to leave. Whereas she goes in and she starts going from one aisle to the other, interacting with different items in there. So I'm ready to leave and she's interacting with the different items. So we got separated. So, but she won't come out. Like, how do I get her out of the store? How do you think I get her out of the store? Huh? I didn't hear that, but it must be funny.
Cinnabon. Cinnabon, like. Cinnabon.
Oh, no, from the store. They don't have that.
What? At the mall?
That's the Justice store.
Oh, just the Justice.
Yeah, so I wanted to come out of the store. So how would I get her out?
You have to buy her something.
You have to buy her something. So she has to take something and walk out with it so that she gets eluted, leaving the store. But we got separated and she got stuck in the store. In order to come out, I had to give her something that will bring her out of the store. That's chromatography. So basically, you have to have an interaction with your, what we call stationary phase. So let's imagine a column. Most of the time in chromatography, it's a column. We'll talk about planar chromatography, which is paper chromatography and thin layer chromatography. But in general, you have a column, and in that column, you have a stationary phase. That means a phase that doesn't move, that is fixed. So that in order to get separation, you need to have some form of interaction with the functional groups on the stationary. If there's no interaction, both compounds or 5 compounds are going to leave at the same time. They didn't interact. So a key for separation is interaction with the stationary phase. So there must be some sort of interaction, and in order to separate, there must be some sort of differences in the way they interact. So back to the store, I don't want to interact, so I'm leaving. The other compound, the other person is interacting, so we get separated. So you want to think about how am I separating my compound? They have to have differences in the way they interact with the stationary phase. Once there is a difference, and once my compounds are interacting, they can be separated. And once they're separated, I can identify, I can detect presence, identify, and quantitate. If they're mixed together, I don't have good analytical properties. I cannot analyze them if they don't get separated. I cannot analyze them accurately. So the first principle is separation. Separation, interaction. If no interaction, no separation, yes. Testing.
Or may I ask, are there still protocols for different columns to be used for different, different things that will.
Absolutely. Question was asking is, will there be different columns to be used for different analyses? There will be hundreds and thousands of different columns. We call them different media, separation media, that with the columns, either you pack yourself, that would be in low pressure chromatography, or they are pre-packed. And oftentimes when you're doing analytical type of work, you purchase columns already pre-packed with the stationary phase that would suit the type of separation. So if you're separating caffeine, for example, which you will be doing in the lab, you would need a specific column called C18 column. We'll talk about that when the time comes. If we're separating carotenoids, for example, we use a column called C40. The C means number of hydrocarbons. So the column in functional group has an attachment. If it's C18, that is 18 carbons. If it's C40, 40 carbons. The more you have carbons, the more hydrophobic your media is. And then that would be meant for hydrophobic compounds to separate. Okay, so this is all things we're going to talk about in much more detail, much slower, and all of that. But I wanted you to grasp 2 important things to start with: separation, interaction. So the compounds need to interact in order to be separated. No interaction, there's no separation. Okay. Very simple concept to keep in mind. All right, let's see what you know or remember, and it's okay if you don't know. That's why we're going to cover all this. So we said interaction. So interaction is important. What types of intermolecular interactions are responsible for adsorption chromatography? Adsorption chromatography is a form of chromatography that we'll be talking about. Do you have any idea at all? Alyssa? All of the above, yes. We will be talking about adsorption chromatography that would involve all of these. Some adsorption chromatography is called hydrophobic interaction chromatography, so it will involve only hydrophobic interactions. So yes, the molecules will interact with your, yes.
I just never could understand or grasp the difference between absorption and adsorption.
Oh, adsorption is when, okay. Absorption and adsorption. Absorption when you have a surface and store the surface. Absorption is when it goes from one surface to the other. it gets absorbed, like in our intestine, we absorb
Okay.
the nutrients. They go into the wall of the intestine and they go inside into the bloodstream. That's absorption.
Absorption is just,
Absorption, stick to the wall, stick to the nutrients.
okay, thank you.
Yeah, but that's a good point. All right. So you'll hear me say reverse phase chromatography, normal phase chromatography. Do you have any idea if we're running reverse phase? And let me explain. Elute is like leave the column, leave the system. Elute, leave. So in reverse phase chromatography, what do you think happens? Which one of those? You don't have to know, otherwise you wouldn't be taking this class, but some of you might have seen this somewhere else. Do you have your hand up? B and C. I don't want to tell you a flat no. It's a good guess. Larissa? Yes, it's A and C. Why? I'll explain that later. But in reverse phase chromatography, your stationary phase is non-polar, and your mobile phase is polar, more polar. So stationary phase, again, is the phase that is not moving, stationary within the column, doesn't move. Mobile phase is the phase that goes through the column and moves, and then your compounds are moving with it. So that's the difference when you say stationary phase and mobile phase. And in reverse phase chromatography, we have a non-polar stationary phase and a more polar mobile phase. In that case, your polar compounds do not like to come, does not like to interact. It's me in the justice store. So I just want to move along and leave. So they don't want to interact with the compound. So they leave first. The mobile phase is polar. Okay. So that's what happens in reverse phase. Now, some would wonder, why is it called reverse phase? It's very simple and really not very smart answer, because originally it was the first chromatography that was based on polarity, separation by polarity. The mobile phase was non-polar and the stationary phase was polar. So that was the original chromatography based on polarity. And then a few years later, they figured, oh, if I swap that, I can separate those that are mostly non-polar compounds. So they came up with that and decided, okay, so this is reverse phase. The other one is normal phase, and this is reverse phase. It's just what started first, and they reversed it. So no smart meaning for reverse phase other than that. Okay, a little bit of history, which I think is good. The first person that ever used the concept of chromatography without knowing it is David Day, who was an American geologist and took crude petroleum and used fuller earth to separate. But didn't really define the principle, didn't really, publicize this type of separation. The person that came next is Mikhail Tsvev, Russian botanist, and he separated pigments, leaf pigments, using chalk. So then he got those different colors of the pigments, different leaf pigments. So he named it chromatography. So chroma for color. Now, not all substances or compounds nowadays we separate by chromatography absorb light. So we use chromatography, but not all of them are based on absorption of light. But still, the phenomena or the separation technique is called chromatography. because the first person that identified the principle separated pigments with colors. So he was credited for the discovery of the separations. And then from there on in the 40s, the partition chromatography was developed and paper chromatography. And we'll talk about partition chromatography next because it's very important, a start for liquid chromatography. In the 60s, because of the petroleum industry, gas chromatography became a thing and got developed much faster than liquid chromatography. And a lot of the knowledge gained through gas chromatography was applied to liquid chromatography and then supercritical fluid chromatography. Okay, so this is it for history. There's more if you want to read about it, but this is just a snapshot of the history. All right, can you give me uses now for chromatography in analytical? Where can it be used? How have you started that?
Could you use it to test for like adulteration?
Absolutely, you can use it to test for adulteration. Melamine, for example, we study later on in the semester under contaminants of concern, you extract and then separate and determine using liquid chromatography coupled with mass spectrometry. Okay, contaminants, good, what else? Shri?
You use it to separate the color pigments?
Pigments, colors, yes, absolutely.
Is it used for characterization?
It used for characterization. So we use it for identification, well, detection, identification, and characterization of structure, Tyler.
Is this what you would use to decapitate something?
Yes, you're going to do a lab on caffeine. So we're going to measure caffeine in different, is that what you said? Caffeine? Yeah. So we're going to look at different beverages and determine the amount of caffeine in these beverages and see if the label gave caffeine justice. Sandy, flavor for GC, obviously. Yes, definitely separation of flavor compounds and determining their identity, their presence, potentially their content. What else? Come on, everything can be marker.
Was thinking something similar, separating fats from non-fats? That's what you do?
Not necessarily. If we're looking at fatty acid composition, then yes, we're going to do a whole GC lab on fatty acid composition in different oils, and we can determine adulteration of oil. So one big example of oil that get normally adulterated is olive oil. So, and sometimes they mix it with something cheaper and they sell it as olive oil. So you're going to determine the identity of different oils based on the fatty acid composition.
Classification of toxic compounds.
Toxic compounds, contaminants, yes, Richard.
To determine relative chemical content.
Relative, yeah, so quantification. So definitely of specific compounds. Great.
Do
Amino acid composition, absolutely. So when we want to determine amino acid composition and determining the first limiting amino acid, which is important for calculation of PV class, which told me that just the correct amino acid score, mouthful, but you have to determine amino acid composition and use chromatography, liquid chromatography specifically. So vitamins is another application. Phytochemicals like carotenoids, hydroxycinnamic acids, flavonoids, isoflavones, examples that you will be separating for the mass spectrometry lab. A whole slew of compounds that are used to separate using chromatography, or the liquid chromatography or gas chromatography, for identification, detection, structure, elucidation, and as well as quantification. Lots of uses. So I'm going to take a step backwards and explain extraction. Why? Because it's the basis of partition chromatography. So partition chromatography was developed based on the extraction principle. So what is the extraction? is transfer of a solute from one liquid phase to another. And that means you have a specific compound of interest, you extract it out of your original sample, you concentrate it in a particular phase so that you can analyze it. So sometimes extraction is means of analysis. That means you extract to determine a specific component. For example, lipid analysis. We're going to study that using Soxley, using Montjomier. So these are methods where you extract a certain component to determine its content. Preliminary sample cleanup. Sometimes if you want to do analysis of sugars and mono-di and oligosaccharides in a particular food, you have to defat first. So you would extract the fat using an organic solvent, hexane, for example, so that you can get to the analysis of your sugars. Concentration of the compound of interest. Flavor analysis, for example, your compounds are very, very small in quantity and scattered. You want to extract them and concentrate them before you can put them in chromatography to analyze them. So these are usually the different uses of extraction. Now, why do we care? Let me demonstrate extraction for you. So first of all, extraction can be batch extraction. So you would have like a separation funnel or a specific flask you will use in fat analysis called the Montjomier flask. So in there, you're putting two different phases, let's say aqueous and organic phase, and then you mix, shake, and then your compound of interest might be in the organic phase. Then you can separate, take the organic phase, and analyze further. Continuous extraction, this is something similar to what we do in the lab with Soxley. Extraction of fat. Continuous meaning, or that particular setup is semi-continuous, but don't worry about it. You have your sample in the tube here inside this compartment. You have the solvent at the bottom. You heat, the solvent evaporates, go up to a condenser, condenses back, solubilize your fat, and siphons back in here. You end up with fat in your organic solvent. So that is a continuous extraction because you heat for a certain amount of time and the solvent evaporates, condenses, go down, evaporate, condenses, go down, carrying with it the fat. Okay, so why is this important? Because counter-current extraction, which I'll show you in a minute, was the basis for partition chromatography. So when you hear the word partition, it means the partitioning of two compounds or more between two different solvents, and they are liquid solvents, obviously. So in this chromatography, your two phases are liquid. So you have two liquid and you have compounds partitioning. At equilibrium, you get what is called as partition coefficient, which is constant. And it is at equilibrium, it means the concentration of solute, one of your compounds that is soluble, is in phase one. And usually phase one in this equation is your mobile, the phase that is moving, over the concentration of the same solute in phase two, which is the stationary phase, or the phase that is not moving. So at equilibrium, there is a specific amount in phase one and a specific amount of that solute in phase two. Okay? So if I have a solute or a compound A more soluble in phase two and solute B more soluble in phase one, they're going to be separate. If they have similar coefficient or partition coefficient, you cannot separate. They have to be different in some way so that the partition coefficient is different we can separate them. So if solute A is more soluble in this phase, the stationary, and B is more soluble in the mobile phase, which will leave the column first? Yeah. If A is more soluble in phase 2, which is the stationary phase, and B is more soluble in the mobile phase, phase 1, which one will leave the column first, Gretchen? B? B, yes. Okay, let me show you the countercurrent extraction, which preceded partition chromatography. This is what it looked like. Tubes, a set of tubes in series. And what's in these tubes? They are all filled with one type of mobile phase, no, stationary phase, sorry, the phase that doesn't move. They all have the same amount of that stationary phase. And then you add a mobile phase and you have in it your compounds that you want to separate. That doesn't make much sense. Let me show you. No. I want to click on this. All right, let me take that over there. See this guy? He's the one that discovered this. Okay. So this is each tube, and I have the tube in series. And this is a demonstration of what happens. Let's start. So you have A, green, B, red, and the white is your liquid that is stationary. It doesn't, it stays in each tube. And the blue here has your mobile phase, liquid phase that it will be moving. And it has the two compounds that you want to separate. So that is the setup. And look at above here the coefficient, partition coefficient. B has higher partition coefficient than A. That means the same as the previous slide. B is more soluble in the moving phase, mobile phase, and A is more soluble in the stationary. So you expect that the B is going to move faster. So let's do that. Let's extract. Let's extract and transfer. All right, what do you see happen? So now in here, I still have more of my A here and more of my B in the second tube, but they're still not separated. There's still some mixed here and some mixed there. So I use another tube. The more tubes I have, the better separation I get. Remember that, because this has to do with the length of your column. When we talk about column chromatography, the longer the column, the more separation you're gonna get, because you have multiple equilibrium. Every tube, an equilibrium happens every time you shake and let it sit, you get to an equilibrium. Okay, this is important when we talk later about theoretical plates. Very important later. Okay, so let's extract again and transfer. So what we're seeing here is your solvent. I don't know why it's red over here and pink over there, but anyway, your B is moving more and the green is retained in your stationary phase more. So I'm going to do this multiple times. Extract, transfer, And you can see what's happening. Slowly, they're going to be separated. Extract, transfer. The more I do that, the better separation I'm getting. And these are forming chromatographic peaks. So I keep doing that, I get separation. The more I do that, the more they're separating, the better is the resolution. That's another word that you'll hear me say quite a bit. The more cubes I have, the more equilibrium I form, the more separation I get. The longer the column, the more resolution or more separation. So I continue to do that until I start seeing the B eluting or leaving the system. So they're very well separated, almost. And look at that here, you start seeing B eluted. So leaving the column or the system until you get 100% of B out before you start seeing a little bit of A. So almost 100% separation. Maybe if we added a couple more cubes, we would have had 100% separation. And then A starts to come out more. This is pretty good separation here. And then all of B is out and then A starts coming out. So you get the idea, right? So this is basically what you will see in chromatography. You will see peaks. We call them chromatographic peaks due to how we are detecting them. So we'll be detecting them using different detectors. Okay, so you'll see chromatographic peaks, and then we'll talk more about them later. So this is a good link if you like to see this happening again. You can, otherwise I'm gonna close out of that and go back here. Okay. So terminology that you will be seeing, hearing quite a bit. Solute for the compound that is soluble. In order for you to run chromatography, your solute or your compound needs to be soluble in something. It has to be in solution, whether it's aqueous or organic. So it has to be in solution, especially if it's liquid chromatography. If it is gas chromatography, it has to be volatile, and we'll talk about that later. But solute refers to whatever is soluble in your extraction buffer or phase or whatever it is, or the analytes. So you can hear solute or analyte. Analyte means the compound that you're analyzing. Stationary phase, the phase that doesn't move. It can be liquid, it can be solid. Mobile phase is the phase that is moving. It's also called diluting solvent because it's the solvent that carries the solute and dilutes them, make them leave the system. Or it can be a carrier gas in terms of gas chromatography. Or it can be a supercritical fluid in case of supercritical fluid chromatography. So series of equilibrium or equilibration, that's what I just showed you in each tube, that equilibration happening. In a column, there will be equilibration happening at each theoretical plate, and we'll talk about theoretical plate later. But the compound, as it moves inside of your column, or it moves down the stationary phase, it's basically going in and out. So there's a mobile phase going in, and the compound moving down is actually moving in and out on the column, on the stationary phase, into the mobile phase going down, interacting with the column, going into the mobile phase. So, and then it reaches equilibrium at different locations. So that's called series of equilibrium. The eluent is what is leaving, the noun of the compound that is leaving, or we can say elute as a verb. So your analyte is eluting out of the column. And the chromatographic peak, which I just showed you, it is related to the mode of detection. Are we detecting based on the amount of current generated? That could be in gas chromatography, in flame ionization detection. Don't worry too much, you're going to be hearing about that. Or is it going to be based on absorption of light? Is it going to be based on fluorescence of light, on refractive index, on molecular weight? So we will get chromatographic peaks based on the detection unit that we have. Okay. So we agree now that chromatography is a separation technique used in many applications of food analysis and other non-food analysis as well. It's based on the partition. Partition is a word used for liquid. When we have liquid, that means a liquid stationary phase and a liquid mobile phase, we use the word partition, or distribution of solute between a stationary phase and another. So if it's a solid and a liquid, then we have a distribution. If it's a solid and a gas, we have a distribution. We have liquid and a liquid phase, then we have partition. So that is the word that you will use for different types of chromatography. Again, this is the partition coefficient or distribution coefficient, which is the at equilibrium, you have to remember, at equilibrium, concentration of solute in the mobile phase or phase 1, concentration of solute in stationary phase or phase 2. You can ask questions, don't be shy. It might be a new topic for some of you or a refresher to others. Yes, Brittany.
So that video we just watched of like the red and the green, that was just extraction, correct?
Yes, extraction using those countercurrent extraction tubes, but the principle of that stemmed into partition chromatography. So each tube later on represent what we call theoretical plate. And we will explain that when we talk about column chromatography, what a theoretical plate is. But it relates to each tube in that countercurrent video that you guys watched. Good. Any other questions? All right. So chromatography, we have different separation techniques. So the terminology is important, you guys. When I ask you in a quiz or in a test, what if you're separating flavor compounds, you're separating fatty acids, you're separating caffeine, what separation technique would you use? You have to tell me. Gas chromatography or liquid chromatography. We're going to talk about supercritical, but there's not going to be an application in this class, but we're going to explain. So often you have to say gas chromatography is the separation technique I'm going to use, or liquid chromatography in the separation is the separation technique. So the separation technique is either gas chromatography or liquid chromatography. Then it gets messier after this. You have type of separation. So we have planar for paper chromatography and thin layer chromatography, planar, and then we have column. We have a column and the phase is in the column instead of on the plane, instead of on a paper or on a glass sheet or aluminum sheet. Then you have the different mobile phases. So in gas chromatography, it used to be called gas liquid chromatography. Why? When it's called gas liquid chromatography, the first word, gas here, liquid here, is for your mobile phase. So in gas chromatography, your mobile phase is a gas. In liquid chromatography, your mobile phase is a liquid, almost always. Always you have a liquid going through when it says liquid chromatography. The second one here is your stationary phase. So in liquid chromatography, stationary phase can be liquid, it can be solid. So in gas chromatography, it is often a solid with a bound liquid on it. So that's why it was called gas liquid chromatography. But you need a solid base, basically. A solid, gosh, I can't think of the name now, but solid substance where you have a liquid either covalently bound or non-covalently bound to the solid surface. And then you have your compound partitioning between the gas and the stationary phase. Okay, so in paper and thin layer chromatography, it's always partition. Always, always. You have liquid mobile phase and liquid stationary phase. So if you have a paper, it will be impregnated with water, for example. If you have thin layer chromatography, you have silica impregnated with water. That's most of the time. So water will be your stationary phase that is held by the paper or the silica. So always mobile phase is liquid, mobile stationary phase is liquid in the planar chromatography. In color chromatography, it can be either, it can be partition or adsorption chromatography. Partition for liquid phase and adsorption when your stationary phase is solid. Any questions there? Too much system overload? I'll be going through this in much more detail. This is just an overview. Okay, so I'll be focusing a lot on column liquid chromatography. I will cover different types, size exclusion, partition, and adsorption chromatography. In either partition or adsorption, it can be a reverse phase or a normal phase. Remember, normal phase is basically the original phase where you had separation based on polarity with a polar stationary phase and a non-polar mobile phase. That is a normal phase. Reverse phase is the opposite of that. Your stationary phase is non-polar and your mobile phase is polar. In adsorption chromatography, you have hydrophobic interaction chromatography. We're going to be covering that. Ion exchange chromatography and affinity chromatography. They are all three. Notice the color of the circle or the arrow here is the same color as that. That means these three are adsorption chromatography. This is an important table for you guys to study from. So here is your method. And under each method, there is a mobile phase and a stationary phase. So it tells you gas liquid chromatography. That means you have gas as a mobile phase and liquid as a stationary phase. Gas solid chromatography, you have solid as a stationary phase. And retention, again, this is a very common name, retention. That means how long it stays on the column or on your non-moving phase. That would be a retention. It's held by your stationary phase. It's to be retained by your stationary phase. So how long it gets retained by the stationary phase depends in different cases on different characteristics. In gas chromatography, it really depends on the molecular size and polarity, and also the thermal stability, that means the volatility of what temperature the compound is volatile at. So this is important. In reverse phase, polarity and also molecular size. The same for normal phase. Ion exchange depends on the charge and the valence of the charge. Size exclusion, only on size. Hydrophobic interaction is how strong it interacts with the hydrophobic surface. So molecular size and polarity and affinity is very unique to structures or specific structures. So this is a good summary table for you to study from. And the last 3 minutes, I'll introduce a gas chromatography, which Gary will spend 2 lectures on, but here's just the principle of it. So in gas chromatography, usually helium is a carrier gas, it's an inert carrier gas, and you have a oven and your column, which is a capillary column, a very long, very thin column. It's very good resolution and very high sensitivity and very low threshold. Don't tell Gary I said that, but I admit it's more sensitive, more separating than HPLC. Okay, so the capillary column, inside of it has your stationary phase. You'll have an injector where your sample is injected, and it moves with the helium, the carrier gas, and gets on the column. This oven heats up, so sometimes you build a gradient where you increase the temperature over time. And what happens then, your compounds get separated based on their molecular structure, size, and polarity. So they interact with the column, and then they get released into the gas phase based on their volatility or thermal stability, at which temperature they become in the gaseous state. So when they become in the gaseous state, they're going to move with the helium faster than another compound based on at which temperature they reach the gas state. And then they move through the column and then to a detector. In this case here, it's an FID detector, which is a very common flame ionization detector. It's kind of like a working horse of GC. So you have hydrogen gas and you have oxygen to generate a flame. And your compounds going through the flame, they turn into ions. And there will be a potential that would be projected across the flame, and then a change in current will be detected. The change in current would be proportional to the concentration of your compound. Concentration and molecular identity of the compound. So you have specific response to different compounds. And then you get your chromatography. So separation is based on thermal stability of the volatiles. You don't want them to be non-stable. You don't want them to degrade. If they are of a low thermal stability, that means they degrade before they get detected. So they have to be thermally stable. They have to be volatilized at particular temperature. And they are separated based on size, polarity, and boiling point, which is the point at which they get into the gaseous state. So this is gas chromatography in 5 minutes, but you'll get 2 lectures from Gary on gas chromatography, and we'll continue on Wednesday. Where do I do this? Hold on. I need to. That's the stuff.
Oh, it's okay. Actually, I
I
can
should have. I should have stopped sharing before I. Stop sharing.
I did not.